So with partial fractions yesterday, we saw that all of these fractions end up with either a linear factor or a quadratic factor. But some of these quadratic factors can't be factorised. So let's see how we handle quadratic denominators, the things that can't be factorised. Well, they might be able to. We can still use this technique even if they can be factorised. These are the integrals we need to know in order to do this. These are all the possibilities we could have. Because every quadratic we could complete the square on and end up with some constant squared plus or minus some factor squared. So the first one with the difference of two squares. Now, we can factorise the difference of two squares, and then yes, we could do it via partial fractions. But save yourself some time, remember these. So they're both 1 on 2a, the log, and then you'll see you've got the factors in the fractions themselves. Now, I'll talk about this a bit more at the end, how I remember them, but basically how it starts and finishes tells me how it starts and finishes here. As I say, I'll mention more about that later. So those two, worth remembering. Then you've got the ones that are on the standards. So if you have the two squares added together, well, that's inverse tan. But what about if it's the square root of a quadratic? And we've seen the inverse sine one, that's not a problem. A squared minus x squared. But then there were these ones that I think I showed you. If you've got 1 over the square root of x squared minus a squared, or x squared plus a squared, again, they're very similar, but it's the log of x plus whatever the square root was. That allows us to handle any type of quadratic denominator. So x squared plus 4x plus 9, well, 5 on it. Doesn't really matter what the constant is on top. We complete the square. So I get x plus 2 squared plus 5. So I've got a situation where it's x squared plus a squared. Well, that's inverse tan. So 1 on the square root of 5, inverse tan, x plus 2 on the square root of 5. But this integral was 5 times that. So we get root 5 times the inverse tan of x plus 2 on root 5. Well, let's have a bit more fun. We've got 3x plus 2 on the square root of x squared minus 4 plus 1. To do this, I split it into two integrals. Okay, let me explain how I've split it. The first one, I've created the derivative on top. So I have a look at the quadratic and say, what is the derivative? And I just put that on top. That automatically means I get du on root u, which I know the answer is 2 root u. Obviously, I can't change the question, but you just look at the x's at this stage. It was 3x, I made it 2x. So to balance it out, it's 3 on 2. But what have I done with the constant then? The constant I've made negative 4 times 3 on 2, which is minus 12 on 2, which is negative 6. But my constant was actually 2. Therefore, in the second fraction, I have 8 on the top. So I now have two integrals. The first one, as I say, I can handle with du on root u. The second one, I will complete the square to see what type of quadratic denominator that we've got. If you don't see the du on root u, then of course you could do a substitution. U equals x squared minus 4x plus 1, and it will come out. All right, so there's the du on root u. 8x on x minus 2 squared minus 3 that becomes. So that is in the form x squared minus a squared, or the square root of x squared minus a squared. So that was the log one. So it's the log of x, or in this case x minus 2, plus, and then you just match the square root. Now I didn't leave it in the completing the square form, I just went back to what the original square root was. I've still left it as root u, hang on. Let's put the u back in. And there's our final answer. So 3 root x squared minus 4x plus 1 plus 8 log x minus 2 plus the square root of x squared minus 4x plus 1 plus, of course, a constant. Now you look at this one and you think, well, hang on, have you gone crazy? That's not a quadratic denominator. But I turn it into one by doing something sort of familiar. Instead of rationalising the denominator, I'm going to rationalise the numerator. So I multiply top and bottom by the square root of x plus 3. And what that does then is creates a question like we just had, where I've got a linear factor on top, and on the bottom I've got, well, in this case, the square root of a quadratic. All right? I'm going to split it up into two things. I create the derivative. The derivative would be minus 2x minus 1, but we have x, so to balance that out, minus a half. But what have I done with the constant? So the constant now is minus a half times minus 1, which is plus a half. We want to get to 3. So I've got to add another 2.5, which is 5 on 2. I have no idea why I put the 5 inside the integral and the half outside the integral. I don't know. I mean, why didn't I just put 5 on 2 out the front? It doesn't really matter, I suppose. So again, I've now created du on root u. Excellent, I can handle that. I've got to complete the square in the second one. But again, if you don't see the du on the root u, you can do it via a very simple substitution. Let's complete the square. This one's a little bit nasty because we end up with fractions. Always hate it when that middle term's an odd number. So much nicer when it's even and you can just halve it. Now be very, very careful when you factorise this one because it's minus x squared. So you've got to think about the factor. I must have had a minus outside of that factor squared, because when I expand it out, I want to end up with minus x squared. But also when I expand it out, I want to end up with minus x. So therefore it needs to be a plus a half in there. Because when we expand that out, we get twice the product, but then I'm going to be multiplying it by a negative. So it's actually x plus a half squared in there. That gives me a constant of minus a quarter. We need to get to 6. So I've got to add in 4 1/4, which is 25 and 4. It's in the form a squared minus x squared. That's just our inverse sign, isn't it? So there we go. So my du on root u is 2 root u. And, that looks awful. 2 outside of x plus a half. I'm not going to leave it like that. I mean, we expand that out. It looks so much nicer. 2x plus 1. We'll write that as 2x plus 1. And we get the root, again, 6 minus x squared. Just a note on that. In this working out here, I've written du on root u and 2 root u. You don't have to. All right, because if you see it and you know, oh, well, it's going to be 2 root u, well, you know what the root is because there it is. So you just go, oh, well, it's 2 times that. The missing standard integrals, these ones. So I said I'd explain how I get this one. So there's the first one where it's a squared minus x squared. X is the key. You see how it finishes with x. Therefore, the answer should finish with x. And when I say finish, I imagine that I'm writing my fraction by, I'll write the numerator, then I write the denominator. Not just finish with the x, but finish with the minus x, because it's minus x squared. So if that's the case, if I finish with a minus x, then I must have started with a plus x. So the other one, it starts with the x. Therefore, this one will start with the x minus a. So x minus a over x plus a. And they've both got 1 on 2a out the front. So that's how I remember them. Now, whether you think that's easy and logical, or whether you just think my mind works in strange ways, no, that's up to you. I mean, we'll add in just a handful more integration questions to look at.